Hello, everyone. So last time we talked about propositions, if you remember. The last time, propositions. So what was a proposition? We said it's a declarative sentence that can be determined as true or false. And then the notations that we use with small letters, P, Q, R, S. And then we also looked at the operations. Such as a conjunction, disjunction, right? Implication, and other operations. Then we also looked at equivalence or logical equivalence. Logical equivalence of, let's say, two compound propositions. So if you remember, we said to find out whether two compound propositions are logically equivalent or no. The easiest way to do that is use the truth table. So we can construct a truth table where each row corresponds to a certain situation for truth or false values of, let's say, P and Q. Now, if for each row, the corresponding column for two compound propositions are exactly the same, then we can say that those two compound propositions are logically equivalent. And we provided some examples. And the last thing we tried to do last time, I gave as an exercise, was what we call it De Morgan's law. So we are going to cover that today as well. But before that, let me give you a definition first. So definition, we say that a proposition, a compound proposition, is tautology denoted by, so let me denote it by curly T if it is always true. Always true means what? Means because it's a compound proposition, right? So it could be depending on the truth values of the components. It could be sometimes true, sometimes false potentially. But if it's always true, then we say it's a tautology. So regardless of truth values of its components. Similarly, or let me give the next definition, a similar definition, a compound proposition is called a contradiction denoted this time by curly F if it is always false. Okay, so for example, P disjunction negation P. In other words, a P or negation P. So this is a compound proposition, it has two parts, P and negation P, and they're connected with disjunction. So this is always true, right? So this is a tautology. because no matter whether P is true or false, P disjunction or P or negation P is always true, right? So see if P is true, then we have a true disjunction false, which will be true. And if P is false, then you will have false disjunction true, which will be also true. So for example, you can think about if P is, for example, it's raining today. Negation P will be it's not raining today. So it's raining today or it's not raining today. So this is always true. Right? It's raining today or it's not raining today is always true. So this is a tautology. And what about an example of a contradiction? Let's say P conjunction negation P is a contradiction. Because again, for example, you can think about it's raining and it's not raining. This has to be always false, right? It's raining and it's not raining is always false. So again, if P is true, then we would have true conjunction false, which will be false. And if P is false, then we would have false conjunction true, which will be also false. Okay, so now let's look at some identities. So some identities, or in other words, logical equivalences. So there is a list in your book. You can take a look at the list and so it's page 29 in your book. So for example, P conjunction and the tautology is logically equivalent with P disjunction. A contradiction is logically equivalent with P. So these are called identity laws. Or for example, P disjunction, the tautology is logically equivalent with tautology. P conjunction with contradiction is logically equivalent with contradiction. These are called the domination laws. And there are other, so the list is rather long. I don't want to list all of them. You can take a look at them yourself. But for example, let's say P, it will list few more maybe. P disjunction P is P conjunction P is P. Or for example, we have commutative. P disjunction Q is same as Q disjunction P. P conjunction Q is same as Q conjunction P. Or we have also, for example, a distributive. P conjunction Q disjunction R is same as equivalent, logically equivalent with P conjunction Q disjunction P conjunction R. P disjunction Q conjunction R is logically equivalent with P disjunction Q conjunction P disjunction R. Or associative. P conjunction Q conjunction R is same as P conjunction Q conjunction R. P disjunction Q disjunction R is same as P disjunction Q disjunction R. De Morgan, what we gave last time as exercise. So P, so negation, P disjunction Q is same as negation P conjunction negation Q, and negation P conjunction Q is same as negation P disjunction negation Q. Okay, another important thing, 8, P implies Q is same as negation P or Q. Another one, P implies Q is same as negation Q implies negation P. So this one, number 9, we cited last time that an implication is always logically equivalent with its contrapositive. Negation Q implies negation P is called contrapositive of P implies Q, and they're always logically equivalent. If you remember the example we provided last time, if it's Monday, then I'll go to the mall. The contrapositive is if I don't go to the mall, then it will not be a Monday, right? Because if it was a Monday, I would go to the mall. So these two are logically equivalent. Number 8 is also interesting, you know, an implication. The left-hand side, there is an implication. Right-hand side, there is no implication. It's just a disjunction. And these two are still logically equivalent. So let's think about number 8 in the context of the example that I just provided. Okay, so we said that, you know, if it's Monday, if it's a Monday, then I'll go to the mall. So if you think about 8, the equivalent would be it's not a Monday, or I will go to the mall. Right? So again, I repeat one more time. If it's a Monday, then I'll go to the mall is equivalent with it's either not a Monday or I will go to the mall. Because if it's a Monday, then I'll go to the mall, right? So either it's not a Monday or it's a Monday, in which case I'll go to the mall. So this is like the more detailed version. But if I want to summarize this, I can also say it's not a Monday or I will go to the mall. Okay, so these are just, this is just an example of 8, but for any of these identities, if you want to prove them, again, the easiest way is to use the table, the truth table, right? So proofs, exercise, use the truth table. Okay, so for example, let me do one of them and then I can leave the rest as exercise. For example, this one, the De Morgan's law. So for 7, negation of P or Q is logically equivalent with negation P and negation Q. So I can draw the table P, Q, negation P, negation Q, P or Q, negation P or Q, and negation P and negation Q. So again, we have 4 possible cases, both true, true, false, false, true, and false, false. Okay, and then if P is true, negation P will be false, false, true, true, and this one will be false, true, false, true. And P or Q, if P and Q both true, P or Q will be true. True or false will be true, false or true will be true, false or false will be false. And the next column is negation of P or Q. Right now, I already have P or Q. I know the column. I just need to look at the last column that I wrote here and just negate it. Every truth becomes false. Every false becomes truth. True. So true becomes false. True becomes false. True becomes false. False becomes true. And finally, negation P. Well, negation P, look at this one. This is the column for negation P. This is the column for negation Q. And then I want to look at negation P and negation Q, conjunction negation Q. So again, one proposition and or conjunction, another proposition. The result will be always false, except the case that both of them are true. In that case, it will be true. So if both the first one and second one are true, true and true will be true. Otherwise, it's false. So let's look. So in the first row, I have false and false, which is obviously false. Second row, false and true, false. False and false, false. And oh, sorry. So this one, negation P. Negation P is the opposite of P. So P was T, T, F, F. So negation P would become F, F, T, T. Right? So this will become F. So let's do it one more time. F and F is F. F and T is F. T and F is F. And the last row is T and T, which is true and true is true. Now let's look at this column. So again, what is the goal here? I'm proving this identity. Negation P or Q is logically equivalent with negation P and negation Q. So negation of P or Q means this column. I have to compare it with this column. Are they exactly the same in each row? Yes, they're exactly the same. F, 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 T, F, 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 T. So these two are exactly the same. So that means negation P or Q is logically equivalent with negation P and negation Q. So like I said, well, I did this one, but the rest are also similar. Use the truth table and try to prove them by yourself. And there are still more identities in your book. Like I said in page 29, there are more identities. So you can also try to prove them as more exercise. All right. So then the next section, 1.4, predicates and quantifiers. Okay, so what is a predicate? A predicate is basically a part of a sentence that states a fact which can be true or false about a property of an object or few objects. So far the propositions that we said were not dependent on any particular object. So we said, for example, each week had 7 days, or I go to the mall. Now, if I say, for example, a person goes to the mall tomorrow, for example. Well, that depends on the person. For some persons, this statement is true. For some persons, this statement is not true, right? So that's why in this type of situation, we need a predicate. So a part of sentence states a fact or about the property or properties of an object or objects or a person or some people. Now that property or that part of sentence is either true or false, depending on the type of object or the type of person or the type of number, depending on the context. So the notation here would be P of X. So here, P is the predicate. And X is the object in the context. Or let's say if it's about a property of two objects or two numbers or two people, we could have, let's say, P of X and Y or Q of X and Y. So here, again, P would be predicate. X would be, for example, the first object in the context. Y would be the second object in the context, and so on. So for example, P of X could be, the person X will go to a mall tomorrow. Okay, or another example, let's say, now again, this sentence could be true for some certain people and false for some certain people. Or another example, let's say P of X could be X squared equals 1. Or let's say it could be x squared bigger than 1, or x squared bigger than 1. Because again, for these statements, x squared equals 1. Well, is it true or false? See, try to compare it with the examples we saw last time. So for example, last time we said the type of example we saw last time, we said, for example, 2 is bigger than 1. Well, 2 is bigger than 1 is true, or 0 bigger than 1 is false. So there is no doubt about it. Or they don't depend on a certain number or variable appeared in the proposition. But when you say x squared equals 1, well, this proposition is true for some values of x, namely x equals 1 and x equals minus 1, and is false for the other values of x. Or similarly, x squared bigger than 1 is true for certain values of x and false for certain values of x. Maybe I write this one as a separate example. Just p of x okay, so let me write this one. So this is, so p of x is true if x equals 1 or x equals minus 1. P of x is false for other values of x. This one here, p of x is true if x is bigger than 1 or x less than minus 1, right? The solution for this inequality is a simple pre-calculus question. The solutions for x squared bigger than 1 is x with the values of x bigger than 1 and values of x less than minus 1. And p of x is false if x is bigger than or equal to minus 1, less than or equal to 1. First, so for numbers within minus 1 to 1, p of x is false. And for the other values of x, namely x bigger than 1 and x less than minus 1, p of x is true. Okay, so this is about predicates. Now let's look at quantifiers. Quantifiers. So we have few important quantifiers in mathematics, which appear in different fields and contexts. So one of them is called universal quantifier. So we say that for each x, p of x is true if p of x is true for every x in the context. And we say it is false if p of x is false for at least 1x. Okay, so first of all, normally x is, we have a statement depending on x. Now, this x could be, numbers. In the case of numbers, normally we can assume that x is a real number, or x could be coming from the set of, if x is a person, in that case, comes from the set of, let's say, people in the world, right? So there is normally a set which is usually called the domain, where x is chosen from that domain. And now if for every x in that domain, p of x is true, then we can say for each x, p of x is true. And when can we say that for each x, p of x is false? If for at least one x, p of x is false. This makes sense, right? If I say, for example, let's say in Math 120 class, let's say we have one student, even if you have one student with, let's say, average or GPA 3.4, let's say, and let's say even if the rest of the students have GPA more than 3.6, for example, still, like if I say for every student in the class, the GPA is more than 3.6, then this statement is false, because for one student, the GPA is less than 3.6. So then the statement will be false. But if it will be true, if for every student in the class, the GPA is more than 3.6, then we can say for each x, for each student in the class, the GPA is more than 3.6. Okay, so let's look at an example. Let's say if I say for each x, x squared bigger than 0. So this statement is false, right? If this is true for every x, every real, here, x is not mentioned, it's coming from which set. So as I said, if x is a number, we can assume, and if it's not mentioned that it's come from a specific set, we can assume that it comes from the set of real numbers. So if x is a real number, x squared is bigger than 0. Well, this is true for almost all numbers, but there is one exception, and that is x equals 0, right? Since for x equals 0, we have x squared equals 0, which is not bigger than 0. So if your statement is false, even for one x, then the statement for each x, p of x will be false. So this statement is false for one value of x, which is 0. So for each x, p of x will be false. Okay, but if I say, for example, for each x, x squared is bigger than equal to 0, then this will be true. Because for every real number x, x squared is bigger than or equal to 0. Okay, another important quantifier is existential quantifier. So this one, the notation is this. So we say there exists x, p of x is true if p of x is true for at least one x. So I don't say one value of x because, like I said, x could be a person. So, but at least one, if at least for at least one x coming from the domain, p of x is true, then we can say there exists x, p of x is true. And when can we say it's false? And we say there exists x, p of x is false if p of x is false for every x in the context. Again, think about it. When can I say that? This sentence, for example, there exists a student whose GPA is bigger than 3.6 is false. If every student in the class, let's say we are talking about the students of Math 120. When can I say there exists a student with GPA more than 3.6 is false? If every student in this class has GPA less than or equal to 3.6. If every student in this class has GPA less than or equal to 3.6, then I can say there exists a student with GPA more than 3.6 is false. Or let's look at also a mathematical example. Let's say, for example, there exists x with x squared equals -1. So this statement is, so can assume that x is a real number. So this statement is false, right? Because x squared is bigger than or equal to 0 for every real number x. So I can say that x squared equals -1 will never be true for any value of x. And therefore there exists x with x squared equals -1 is false. Well, as you may know, x squared equals -1 could happen if x comes from the set of complex numbers. But in the college level, almost in all courses, we can assume that x or our numbers come from real numbers. There's only some exceptions in the set, for example, differential equation course. There could be some cases where your number comes from complex numbers. But other than that, you can always assume the college level that the numbers come from the set of real numbers. And if x is a real number, x squared is always non-negative, and therefore it will never be equal to -1. So I can say there does not exist any x with x squared equals -1. Okay, so the notation that we use in this case, notation, there does not exist x with x squared equals -1. So this notation, if you see it, it means there does not exist. So this one means to write it this way, read, there does not exist x such that x squared equals -1. So since there exists x with x squared equals -1, we established that it's false. Again, of course, assuming that x comes from the set of real numbers, then this will be true. So note, since there exists x squared equals -1 is false. You can say there does not exist x with x squared equals -1 is true. Okay, and another quantifier is called uniqueness quantifier. We say there exists unique x with p of x is true if p of x is true for exactly 1x, and otherwise we say there exists unique x with p of x is false. So if p of x is true for exactly 1x, so please compare this with the previous case. that where we said it's true if P of X is true for at least one X. For the case of the exists X P of X, we need P of X to be true for at least one X. But in the case of there exists unique X with P of X, we need P of X to be true for exactly one X. And you can guess this from the name, right? It's called uniqueness quantifier. So there should exist a unique X where P of X is true, so that we can say that the statement is true. So in that case, if there exists exactly one X, we say it's true. If there exists exactly one X such that P of X is true, we say this statement is true. Otherwise, we say it's false. Otherwise means what? Means either P of X is not true for any value of X, or it's true for more than one value of X. Right? So for example, when can I say that there exists exactly one student with GPA more than 3.6 is false? If there is no student with GPA more than 3.6, or if there is more than one student with GPA more than 3.6. In those cases, I can say this sentence is false. So let's look at an example. There exists unique X with X squared equals 1 is false, right? Since X squared equals 1 holds or is true for two values of X. Two values of X, namely X equals 1 and X equals minus 1. For another example, let's say there exists a unique number P such that P is prime and P is even. So in the context of prime numbers and even numbers, well, remember we said that depending on the context, the number is chosen from a particular set. But in the context of prime numbers, even numbers, we can assume that that set, which we call the domain, is the set of integers. When we talk about prime numbers and even numbers, that means we're talking about integers. So is this true? There exists a unique number that is both even and prime. The answer is yes. So this is true. There is only one number, one integer, which is both even and prime, and that number is P equals 2, right? So since P equals 2 is the only integer, or is the unique integer that is both even and prime. Okay. Now let's talk about the negations. So for example, negation of for each X P of X. Negation, if you remember, means it's not the case that. So when can I say that it's not the case that for each X P of X holds? Again, think about the example we did. When can I say that it's not the case that for each student in our Math 120 class, their GPA is more than 3.6? under which circumstances I can say it's not the case that for each student in Math 120, their GPA is more than 3.6. If there exists at least one student whose GPA is less than or equal to 3.6. If there exists at least one student with GPA less than or equal to 3.6, then I can say it's not the case that for each student, their GPA is more than 3.6. So this is logically equivalent with there exists X with negation P of X. So similarly, the negation of there exists X with P of X. Again, think about it. Oh, this one, it seems that it's, okay, yes, right. When can I say that it's not the case that there exists X or there exists a student in our Math 120 class whose GPA is more than 3.6? It's not the case that there exists a student with GPA more than 3.6. When can I say that is the case? Under which circumstances? If for every student in the class, the GPA is less than or equal to 3.6, then I can say it's not the case that there exists a student with GPA more than 3.6. So this is logically equivalent with the, for each X, negation P of X holds. Okay, so negation of for each X P of X is there exists X with negation P of X. Negation of there exists X with P of X is for each X, negation P of X holds. So let's look at an example. Negation of for each X, let's say X squared is bigger than equal to 0. What is this according to what we said? The first one, we want to use the first identity. Negation for each X P of X is there exists X with negation P of X. Negation P of X means X squared not bigger than equal to 0. P of X says X squared bigger than equal to 0. Negation P of X would be X squared not bigger than equal to 0. Which is same as saying that there exists X with X squared less than 0. Right? Not bigger than equal to 0 means less than 0, right? It's a very simple mathematical fact. Not bigger than equal to 0 means less than 0. So, and one way to verify your answer is that, please remember that if you have a proposition P, negation P has the opposite truth value, right? So if P is true, negation P will be false. If P is false, negation P will be true. So let me write as a remark or note that for each X, X squared bigger than or equal to 0 is true. And negation of it, which as we said is same as there exists X with X squared less than 0, is false. There exists X with X squared less than 0 is false because there is no X that X squared is less than 0. And that's exactly what we expect, right? We expect that if the original proposition is true, then the negation of it is false, should be false.